recall back in Calculus 1, a function f is differentiable at a point A if there was a tangent line to the curve at the point A, f of A. Now, a function g is not differentiable at B if there was no tangent line at the point B, f of B. Now, we want to look at an analogous idea to a surface. So look at a point in the domain of a surface. The domain of this function f are points in the xy plane. So the point AB in the xy plane will have a point AB, f of AB up in the surface. Now the function g is differentiable at that point AB if there's a tangent plane to the surface at the point AB, f of AB. G is not differentiable at a point CD if there would not be a tangent plane. So there is no tangent plane at this point, CDG of CD. Okay, for it to be differentiable, it needs to be a smooth curve at that point. Okay, now we have two different ways that we might be given the equation of a surface. One is an implicit definition. Where you have a function of x, y, and z equal to 0. The other one is an explicit definition for the surface, which would be z equal a function of x and y. So the first way that we're going to get an equation of a tangent plane will be looking at the function if it's defined implicitly. Okay, so now every point on the surface must satisfy this definition. So what we'll do is we'll take a curve that's located in the surface. So this curve C has every point on that surface. So that means every point on that curve satisfies this equation. So now, I want to take this equation and I want to differentiate both sides. The left side, I've got that function f has three variables, x, y, and z, and each of those is a function of t. Now this curve C is defined by this vector valued function. R of t, it's a function of t, is the x of t, the y of t, and the z of t. So I see that x, y, and z each depend on t. Now if I'm differentiating this equation, the left side then uses the chain rule and becomes the partial of f with respect to x times the derivative of x with respect to t plus the partial of f with respect to y times dy dt plus the partial of f with respect to z times dz dt. And then the derivative of the right side is just 0. Now I can rewrite that and look at that as a dot product. That's the partial of f with respect to x, the partial of f with respect to y, and the partial of f with respect to z, dotted with the vector dx dt, dy dt, and dz dt. Now, dx dt, dy dt, dz dt is just r prime. So the vector given by x prime of t, y prime of t, and z prime of t is just the tangent vector. Okay, so what this says is that the tangent vector of that curve, that was just a random curve on that surface, is orthogonal to the gradient. Now I can choose any curve on that surface. I could have a curve going this way, going this way, going this way. Any curve on that surface that goes through the point P naught has a tangent vector that's orthogonal to the gradient. So each one of these tangent vectors is orthogonal to the gradient. Now look at the plane that contains all of those tangent vectors. The plane containing all those tangent vectors will be orthogonal to the gradient. Okay, that plane is called the tangent plane. So the tangent plane is formed by taking the tangent vectors for all the curves C that pass through the surface through the point P naught. So now, if I want the equation of that tangent plane, what I need to get the equation of a tangent plane is I need a normal vector. Okay. Now that normal vector, the vector that's orthogonal to the plane, is the gradient. So that normal vector will be the vector given by the partial of f with respect to x at ABC, the partial of y of f with respect to y at ABC, and the partial of f with respect to z at ABC. So that's our normal vector. The point P naught is the point ABC. Okay, so now just to get the equation of the plane, I'm going to take just a random point here on the plane. So I'll call it x. And in vector form, that point would be x, y, z. Or you can think of it as the point x, y, z. The vector passing through the point P naught and x would be given by x minus a y minus b and z minus c. That's a vector in the plane because the plane passes through the point P naught ABC and x is just a point on the plane. And we know that any vector in the plane must be orthogonal to the gradient. So we'll have that f, I'll just look at it right here. Here's the gradient dotted with this vector would be the first component times the first component here, plus the second component here times the second component here, plus this component times this component. So we took the dot product of the gradient and the vector x minus a, x minus or y minus b, and z minus c. And that dot product has to be 0 since every point in that plane is orthogonal to that gradient. So this is the equation of that tangent plane. It's real simple to get. Get your point, ABC, get your gradient at that point. So here's the first component of the gradient evaluated at ABC, the second component of the gradient, and the third component of the gradient, and then just multiply by x minus a, y minus b, z minus c, and that product has to be 0. Okay, so now let's apply it. We need our normal vector and we need a point. I want the equation of the tangent plane at this point. So we've got our point. This is our ABC. And now we need to find our gradient. The gradient of f partial with respect to x is 2/9 x. The partial with respect to y is 2 over 25y. The partial with respect to z is 2z. So now evaluate the gradient at the point. So the gradient evaluated at 0, 4, 3/5 will be the vector 0, 8 over 25, and 6 over 5. So now, the equation of the tangent plane. This is our normal vector. This is the point. So our equation of the plane will be 0 times x minus a plus 8 over 25 times y minus b, which will be y minus 4. So this first one was x minus 0. So here's the point. So it's x minus 0, y minus 4, and z minus 3/5. And then our other, here's your normal vector, the next component of the normal vector, and then my last component of the normal vector. So put the normal vectors as the coefficients of x minus the 3 components here, the point minus the components, and that has to equal to 0. So now if you want to simplify that, you can expand it, make it 8 over 25 y plus 6 over 5 z. I would have 32 over 25 plus 18 over 25. So that ends up being 50 over 25, so just 2. And if you wanted to get rid of the fractions, you could multiply everything through by 25. You would have 8y plus 30z equal to 50. Now notice there's no x value in that definition of the plane. That means that the plane is parallel to that x-axis. So this is the equation of that tangent plane at the point 0, 4, 3/5. Okay, so now at what points on this ellipsoid, the definition of this graph would be an ellipsoid, at what points on the ellipsoid will the tangent plane be horizontal? Well, if a tangent plane is horizontal, that means that the gradient is vertical. So what does a gradient look like if it's vertical? If it's pointing straight upward, the gradient then needs to be of the form 0, 0 in some number. Well, we got that the gradient had this form. So for what points, what would the x and y, z values be if that gradient were going to also be of this form? Well, that means that this first component must be 0, the second component must be 0, and then the third component's just some other number. So for the tangent plane to be horizontal, 2x over 9 is 0, which means that x is 0, and 2 over 25 times y must be 0, which means that the y value has to be 0. So the points on the ellipsoid where the tangent plane will be horizontal will be points of the form 0, 0, and some z value. So now what would that z value be? Well, let's find it by evaluating the equation. So if you put 0 and 0 for the x and the y, you'll have 0 plus z squared minus 1 equal to 0, which means that the z is either a positive or a negative 1. So the points on the plane where the tangent plane is horizontal will be 0, 0, 1 or 0, 0, -1.